Hello everyone, today we are going over the blind 75 in C++, and today we are working with the problem house robber. Now, before we get started, if you're following along at home or wherever, feel free to pause the video. For whenever we are dealing with these four questions, we always need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, just breaking down the problem right now. Again, feel free to pause the video if you're taking time to write these questions. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. All houses at this place are arranged in a circle. That means the first house is the neighbor of the last house, Meanwhile, adjacent houses have a security system connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Okay, so we already know exactly what we have. We are given an integer array called nums. And we need to return the maximum amount of money you can rob tonight without alerting the police. And so if we were to go over the example to help illustrate the point, I'll also have a visual in the video as well to help describe. So if we have a house, in this nums array, we have three houses with the amount of money 2, 3, and 2, and we need to find the maximum sum of all the following houses accordingly. And it looks like that we can only rob the house that has the amount of 3, given the fact that we were to rob 2 and 3, that alerts the police, and 3 and 2, that also alerts the police, because we can't rob houses that are right next to each other. You cannot rob any neighboring houses. No, that's why in this example, it looks like we can only rob house 3. And then also, if we were to figure out the index of this following number, if we were to visualize in particular on the houses that are around in a circular fashion, we cannot rob houses that are right next to each other, for this will alert the police, and this will also alert the police, and then this will also alert the police as well. But house 1 and 3, you cannot alert the police, and 2 and 1, you can alert the police, but the maximum sum is 3 and 1. So therefore, when comparing the different sums of each of the following combinations inside of our array, we get 1 and 3, which is 4. Highlighting this example over here. And then we also have a following house as well. We will have 1, 2, and 3. Looks like the maximum amount of money that we can get out of one night is going to be 3. So the technique that we're going to be doing is going to be dynamic programming with 2 sets to scan the array in different fashions. Fashions meaning we will have one scan that will be separate from the other, and I'll explain more in the steps. So the steps for us to be able to generate this behavior as described before, since we need to find the maximum sum of the following house. I'll just give up these primary steps. What we'll do is that we will need to scan our following array and compare each of the values / sums. And so our steps to be able to replicate this entire behavior that we will have and return max are going to be as follows. Step 1, we're going to check if the array is empty. We will return 0 for our edge cases. Then, if the array has only one house, we will return its value. Then, if there are 2 houses, we will return the maximum value of the 2 houses. Now the next step that we will do is that we will create two dynamic programming arrays called dp1 and dp2, which are going to loop through each house from the first to second last. So we're going to be scanning our array, do this first scan from this to the second last, since we want to keep separate scans and we can't rob any houses next to each other. So we're going to do 1 and 3 first, for example, in this scan. Updating dynamic programming array 1, and then we will loop through each house from the second to very last element, updating dynamic programming array 2. And finally, we will return the maximum value between the last elements of dynamic programming 1 and dynamic programming 2 arrays. So, to be able to showcase the steps that we'll be doing, since we have 5 steps, following them over here. Step 1, where we deal with the edge cases, 0, 1, and 2 homes. Step 2, Step 3, Step 4, and Step 5. Step 1, we will handle our edge cases like this. So I'm going to first create n be the nums dot size. Then if n is equal to 0, we will return 0, and n, so n represents the num size, so this represents if the array is empty, we will return 0, and if the array only has one house, so that means n is representing the array's size. So we're going to transfer this to be 1, and we're going to return the very index that is over here. In fact, for clarity, I can just do this. Nums.size. It's still going to be the same thing. And then if the size of our following array is equal to 2, we're just going to return the maximum sum between the very first index that we have of our array nums of 0, and then nums of 1. So we do, and then for step 2, we are going to create our arrays vector int dynamic programming 1 based on the size of our following array, and then we will have our second dynamic programming array. Then for step 3, scanning for first scan with dynamic programming array 1, and then second scan with dynamic programming array 2, return the max sum of both. Compare them. So the way step 3 is going to look, it's going to be this. We are going to have dynamic programming array at the very first index, and nums 0, and then we're going to initialize our max for the first scan. And then for int I is equal to 2, I is going to be less than nums dot size I plus plus, and then we're going to update accordingly our following index for a dynamic programming array that we will be storing while scanning equals max dynamic programming 1 to the second to last. nums of I, since we're getting our max, and then we start comparing between the following values that we have collected to the very last element. And finally, for step 4, we'll do the same thing, except we're dealing with dynamic programming array 2. So, actually, let me make sure that this is correct. 1, 1. So we initialized 1 here, 1 there, yes. And 2, 2, 2, 2. Yep, 2, and then we're going to update our index, so our following will be 0 to start, and then we're going to have nums of 1. Make sure that we have our semicolons along the way, and then we will update. Since we're updating from the second to last. So we will have dynamic programming 2 array update with max dp2 I minus 2 nums of I dp2 I minus 1. Yep. Okay. That's one update, and then finally we'll return max within our 2 dynamic programming arrays with the very last element n minus 2, and then dynamic programming 2 n minus 1. Let me just double check to see if this is all correct. So just want to be sure about this. I've actually made mistake and size. Size minus 2. Yep. In fact, I can even just do the same thing. So int n is going to be num size, and then I can just make this cleaner. So we can just get the picture. There we go, that's better. Cleaner. Alright, now, just double checking on this. Let's close this, let's run it. Alright, it passes all the test cases, let's submit. Okay, now just to give a breakdown on our space and time complexity for our following solution is that the time complexity is going to be O of n, where n is referring to the number of houses that we have. And this is just because we iterate through the list of houses twice. Well, meanwhile, the space complexity is also O of n, since we create 2 dynamic programming arrays with the size equal to the number of houses. So yes, this was House Robber 2. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.